Yeah, and
Great.
slideshow. Now, is it visible?
Yes, perfect. Yeah,
Okay.
it's full screen also. Okay,
Yeah.
so let's move ahead. So our next speaker is Archan Majumdar from the SN Bose Center of Basic Sciences, Kolkata.
Recording in progress.
He's a senior professor there, and his primary interests at the moment are foundations of quantum theory, quantum information, and like our first speaker, he is also trained in cosmology and field theory and particle physics, I believe, and he has made important contributions to the field of quantum foundations. And with that, I would like to welcome you for the talk. Yeah.
Sorry, am I still there?
Okay. Yeah, you are there, but now suddenly it has shrunk your full screen.
Okay, let me just do once again full screen. Is it fine then? Yeah, because
Perfect.
I can't figure out a way of making my view slightly curtailed so that I can also see what is there in the message. Anyway, let's forget it. So let's now my slide is visible.
Absolutely.
And it is changing also?
Yes, it is.
Okay, good. Yeah. So thank you very much, Shaureen, and let me thank all the organizers, Shaureen, Professor Panigrai, and everybody else for arranging this very nice meeting. This is, I think, maybe, I don't know, 5th or 6th in the series of wonderful QIQTs. And I remember nice occasions before the pandemic where we all used to be there and had a lot of discussions. But this is also a very useful mode when people from various parts of the world can come and participate in online mode. So thank you very much, and thanks for inviting me to give this talk here. So today I will be talking on the subject of quantum communication basically, and quantum advantage in communication tasks. And the question we pose here is that what is behind quantum advantage over classical physics in communication tasks, in quantum communication tasks? And we will argue that this is nothing but essentially measurement incompatibility and also contextuality. So I'll be reporting about a couple of works, one which is there in the archive, the first paper, and the other one, which has just appeared in PRL a few weeks ago. And these works have been done with my ex-Inspire fellow Devashish, who is now at ISF Trivandrum, is a faculty member there. Devarshi, who was a postdoctoral fellow here, is now a Newton Cambridge fellow at King's College London. And Arun is a current student. Bihalan was my ex-student who is at ISF Behram. So this work. And the other one is done with my ex-student Shashank, who is now at the QNU Labs. And Devashish, of course, is there. Devashish, who is now at ISF Trivandrum. Zhu in Berlin, and Adam Cabello, many of you know, Seville, Spain. Okay. So I'll be pitching this talk mostly at the level of students because I find that many students are attending this conference. And I would also ask everyone that at any moment, if you have any doubts or questions or comments, please interrupt me. The point is not to take you through the whole bunch of slides that I have collected, but the point more is to actually convey something which can be sort of, let's say, mildly entertaining. Okay, so from what is our perspective for this talk? So let us look back from a slightly aloof manner and try to think of a time when quantum mechanics was invented, that is the early 1900s. And quantum mechanics since then has become a very important founding pillar of quantum physics, one of the very few pillars. And essentially, what were the key elements that actually took quantum mechanics away or apart from classical physics? And these were at least a couple of them: the uncertainty principle, which was proposed by Heisenberg, and the superposition, okay, of say basic physical entities. So these were the two key elements which actually distinctly differentiated quantum mechanics from classical mechanics. And as all of you know, this ushered in the so-called first quantum revolution, and there were huge technological spin-offs. And the most, a couple of important ones, if you like, are to do with transistors, lasers, so on and so forth. Okay, so this brought an entirely new paradigm in the technology that was used by human beings since then. So now what happened then? So this survived for this, I shouldn't say survived, this trend kept on for 70, 80 years. And then in 1990s, okay, around 1990s, something new came in, and this new topic or subject was motivated by some key foundational questions of quantum theory, which were indeed raised, or at least the precursors were raised by the forefathers of quantum mechanics in the early 1900s itself. Now, the study of these foundational issues actually, in conjunction with information theoretic principles, actually brought about an entirely new field, which is called quantum information science. And we have not looked back since then, the last 25, 30 years. And this has ushered in a potential for some entirely new quantum technology. So I just shouldn't say potential, because some of them QKD have already been implemented commercially, and others are in various stages of implementation. So this is no doubt again called the second quantum revolution. So now the question is actually what basically happened between these two steps, which are separated by, say, 60, 70, 80 years. So which actually, I mean, brought about this new revolution, and what is our key physical intuition that we have learned from this second revolution, taking us beyond the first revolution. Okay. So thereby, this is the question, this is the perspective of the talk, this is the question that we raise in the couple of papers I just mentioned. So we ask the question, what is the fundamental or key feature or property of quantum mechanics that sets it distinctly apart from classical physics, and which actually nowadays allows some beautiful information processing tasks which are indeed technologically revolutionary. So we actually ask this question, what is there in quantum mechanics which is not there in classical physics, which enables such beautiful information processing tasks? And we answer this in the following way. We say that among many other things, the prominent role is due entirely to the character of measurements in quantum theory, as different from the character of measurements in classical theory. Okay. So what exactly do we mean by the character of quantum measurements? The character of quantum measurements, well, incompatibility of quantum measurements is a feature which is completely absent from measurements in classical theory. And I'll delve into it, of course, in more details as we go on. And also the second thing, incompatibility inevitably brings out something which is called contextuality. So in quantum mechanics, it is not only that the system you are measuring, which is important, and it reveals its properties in any measurement, but in the fact that what kind of measurement you are using, what property you are measuring, what kind of apparatus, the settings, etc., all form a context. And the properties appear only, or the probabilities of the measurement outcomes only appear due to such context. So again, fundamentally, I would say incompatibility, which also results in contextual. So these two are the two most important things, as we will argue in this present talk. Okay, so here is the outline of the talk. First of all, I'll spend a few minutes by actually describing to you what we mean by measurement incompatibility. This is basically very, elementary level quantum mechanics. So all of you who have had elementary college level quantum mechanics should easily follow it. And thereby, I will come to the motivations of our present analysis and study, especially in the area of quantum communication. Okay. And in quantum communication, the prototype is set by the so-called RAC games or random access games. So again, for the benefit of students who are not aware of it, I will spend a couple of slides describing such RAC games. And then we will actually come to the heart of the talk, and then we will show, as we have proved our result, that incompatibility of measurements is actually necessary for any quantum advantage in any general communication tasks. And I would describe to you what we mean by such communication tasks. So this is the message I would like you to carry away. And then finally, depending on how much time we have, I would come to the next topic of contextuality. And then I would show that if you go one step ahead, that incompatibility, though it provides quantum advantages communication, but if you want to really extract such advantage for practical purposes, then you can easily show, and I shouldn't say easily, it took us a lot of hard work, by the way, but it is possible to show that contextuality is the subject, is the actual property which indeed provide this advantage in communication complexity. And finally, again, depending upon time, I will discuss some applications of contextuality in this context, and one such is the secure semi-device independent quantum key distribution protocol. Okay, so let us start by discussing what is measurement incompatibility. So basically, when we say incompatible measurements, what do we mean? We mean that such measurements cannot be performed simultaneously on a single copy of a quantum system. And everybody is familiar with the very elementary position and momentum that was indeed taken up by Heisenberg in his famous uncertainty principle. So you know that if you have a single copy of a quantum system, you cannot perform a measurement to precisely measure both position and momentum, okay, simultaneously with arbitrary precision. And next, what we describe here is that, and what is the main important message is that it is indeed this, that is measurement incompatibility, what I just discussed to you. This is what actually differentiates quantum mechanics from classical physics at a very basic elementary level. And not only that, it doesn't only distinguish QM from classical physics, but measurement incompatibility is at the very root of many fundamental quantum aspects. And by that, you can have plenty of examples. I mean, many of you have heard of Bell non-locality, MI is responsible, EPR steering, quantum contextuality, quantum violation of macro realism, many kinds of steering, that is temporal channel steering, so on and so forth. So you think of any counterintuitive aspect of quantum mechanics or any interesting aspect of quantum mechanics, and inevitably you can find that the character of quantum measurements, essentially measurement incompatibility, is inseparable from all these very beautiful properties like Bell non-locality, EPR steering, contextuality, so on and so forth. So this is the qualitative definition of measurement incompatibility. And also, before we move on, I must also, for completion's sake, for those of you experts who are there in the audience, I should actually also relate these results which are there before our work. So it has been shown in 2018 that measurement incompatibility is necessary, but it is not sufficient for Bell violation. This is by Brunner's work in 2018. So MI is necessary, but not sufficient for Bell violation. However, for steering, MI is both necessary and sufficient. This is work by Brunner again, PRL 2014. And measurement incompatibility is mostly, brought out in communication tasks which do not depend on entanglement. Okay, so entanglement is a very beautiful thing, and most of the present information theoretic tasks rely on entanglement. However, there are plenty of other tasks as well, which take us beyond classical physics, where no entanglement is required. And I typically mean tasks in the prepare and measure scenario. And one example I can immediately say is the QIQT, say the BB84 protocol. So that doesn't depend on entanglement. But what does it depend on? It depends on measurement incompatibility. And these people actually, Carmeli et al. In a 2019 PRL paper showed actually discussed another very beautiful task, state discrimination, which I think briefly Ujjwal may have also alluded to in his talk. So measurement state discrimination can be shown to follow as a direct application of measurement incompatibility. Now, the point again, as these people discussed, and another paper in PRL by Cavalcanti et al. In 2019, these are the next two, one-to-one papers. And what these people showed that measurement incompatibility is both necessary and sufficient in state discrimination task in the prepare and measure scenario. So these are some of the work which form the backdrop of our analysis, which we are going to discuss now. So based on such prior knowledge, the question that we ask here is that, so these are examples, what I showed you, examples of tasks where measurement incompatibility has been shown to be effective. Now, based on this knowledge, we ask the particular question as follows. So we ask that, is there any generic link between measurement incompatibility and non-classical correlations? Okay, so these are, all of the earlier ones are very specific tasks. But now we ask, is there any generic link at all between this very fundamental property of measurement incompatibility, and many different kinds of non-classical correlations which give rise to different features of quantum information like Bell inequality, steering, okay, and temporal correlation, so on and so forth. And what we say here, we answer this in the affirmative, and we say definitely yes, and we show that particularly in the context of the prepare and measure scenarios, which are scenarios without any use of entanglement. Now, you may ask here why I'm not using entanglement. Of course, in any scenario involving entanglement, one indeed has to prepare and measure. That is there too. But we want to separate out this feature itself, entanglement, from our analysis, so that no one can say that why should MI be responsible, but entanglement is playing the role. So we go one step deeper, we take out entanglement and we discuss only scenarios which are without entanglement, and then we answer in the affirmative this question that there is indeed a generic link between measurement incompatibility and non-classical correlations which give advantage in quantum information processing or communication. And as an upshot of this analysis, we are also able to show that indeed there are operational witnesses of measurement incompatibility. And for those of you students who are not aware of this, what are quantum witnesses? Quantum witnesses are essentially some Hermitian operators which we can measure on any given state, and from their values we can infer the property of those states. Okay, so what we show here is that there indeed exists operational witness of measurement incompatibility for any set of quantum measurements of arbitrary set. Okay, so this is important. Okay, so now let us come to the heart of the matter, the formal definition of measurement incompatibility. And for that, you have to consider a general POVM. Let us say take a set of effects which are labeled by M, and Y is the set of inputs. And whenever we say that any quantity belongs to this square brackets, that means it can take values from 1 to ... up to the last number n. So y belonging to n means y can take values 1 to n. Okay, so y is the set of inputs, and the measurement outcomes are labeled by B depending on the input y. And what we define, how these POVMs are defined, is that all such effects are positive and the sum of them actually adds up to 1. This is the normalization. So now, if we take a set of measurements which are contained in this set, and we say that the set of measurements is compatible, if there exists a parent POVM, so this is a parent POVM which I label by GK, the set of all GK with GK greater than 0, and sum of GK equal to 1, such that for all outputs, that is By and inputs, your measurement effect can be decomposed in this way, that is the sum of probabilities, conditional probabilities of the output given input k and times gk. Okay, and here also you need to take care that these are probabilities, these are automatically greater than 0, and some of them are equal to 1. So what is the meaning of this statement, this equation? So what we mean here is that if there is a parent POVM given by this set of GK, so then the marginals of the parent POVM actually give rise to individual measurement effects, which are labeled by N. So whenever marginals of a parent POVM give rise to individual measurement effects, we say that such general measurements are compatible. Okay, so this is the definition of compatible. And whenever they do not, then they are incompatible. So you can easily look into this and you can understand that in case of incompatible measurements, you will not be able to find such a collective parent set whose marginals will give rise to individual measurements. Okay, so this is the definition of incompatibility. And now what is the connection with communication task in the prepare and measure system? So let us discuss the prototypical communication tasks, which are called, say, random access codes or RAC games. And this is just a two-party scenario where Alice is a party who actually prepares a constant state and sends to Bob, and Bob performs a measurement. Okay. And what are Alice's inputs? And so Alice, this is, by the way, a 2-to-1 quantum random access code, the most elementary quantum random access codes. And Alice has the input of classical bits given by 00011011, and she receives at random any one of these. Okay. And then she encodes this message in a qubit, which is a row. Let us take it in 2 dimensions, and she sends it to Bob. So now what is Bob's task? Bob's task is to actually decode this qubit or answer the question, which of these actually Alice sent to him. Okay. And as an input also, Bob gets these 2, 0 and 1. And so Bob performs measurements depending on his inputs and also on the state row. And we say that Bob has won this game when he is successful in determining Alice's message up to some probability. And whenever that probability exceeds the bound set by the classical limit or the classical bound, which can be derived here, we say that Alice and Bob have been successfully in performing this quantum random access code task. Okay. So in a nutshell, this essentially describes the prepare and measure scenario. One party prepares something and sends to Bob. So this party can be regarded as a black box. We do not know a priori, I mean, what Alice does, whether she cheats, whether she sends a classical system or a quantum system. But depending on the joint probabilities and when the Bob is able to reproduce Alice's message or know Alice's message, Bob is successful. Beyond the classical limit, then the quantum game or quantum task is successful. Okay. So now one can generalize this 2-to-1 RSC game for a scenario of n inputs. So again, this is the typical prepare and measure scenario. So suppose we have a string of n inputs, it can be anything, n did say, and then Alice encodes this inputs, which she receives, one of them randomly, into a quantum state rho x, and the Bob's task is to actually decode which input Alice has encoded. And, yeah, sorry, there is a question. I heard some disturbance anyway. So should I continue?
Yeah, please.
Okay. So Bob's task is to decode, and Bob also receives, say, n inputs given by y. So now this is also not the complete story, because Alice and Bob also may have access to some shared randomness, which could come from a common source SR. And typically these are represented by a series of hidden variables. So this can also be allowed. So this is not something which is excluded. So there could be some common source and some classical randomness can be shared between Alice and Bob. Right. So now we come to the heart of this talk. That is at least the first part of this talk, that we prove in our paper that incompatibility is necessary for quantum advantage in communication tasks. So for that purpose, we consider a communication task, which is a general RSC. And as I said a little bit earlier, so one party here is Alice, and it is a black box. By the way, I am reminded of Ujjwal's picture of Suchitra Sen. So if Ujjwal is still there, and if for those of you who are, old enough to remember, for the last part of her life, Suchitra unfortunately was confined to a black box. We didn't know what happened to her, what she was going through. Anyway, jokes apart. So Alice stays in a black box, and she receives a set of, say, digits or inputs, which can go up to say di, and all these x, by the way, x also are multiple value, can be multiple value. So we are generalizing this scenario, and it can go up to L, and similarly the outputs can go up to N, and Bob, depending on Bob's inputs, that is y, and the message or the quantum state encoded by Alice performs some measurements, generalized POVMs. And Bob's task is to figure out actually which of the particular XY Alice actually encoded. So if Vy equal to XY, then Bob is completely successful. But there are some probabilities of success. So these depends on, what do they depend on? They depend on, of course, Bob's outcome, conditioned on Alice's inputs and Bob's inputs. So again, to repeat, Alice receives some input X randomly, which she doesn't know. She sends the d-dimensional classical or quantum system to Bob. Bob receives input y and the message from Alice, and he outputs some result by depending on his measurement. And this by can belong to up to this by. Okay, and the outcomes are determined by the probability. Okay, so now let us figure out what these probabilities can be. Okay, so what these probabilities can be, of course, depend on what kind of mechanism Alice and Bob are using to play this game. So suppose Alice does not use a quantum state, but actually sends a classical communication, but she also has access to pre-shared randomness. Then what kind of probability will it look like? So then in this case, when there is classical communication using pre-shared randomness, you can easily satisfy yourself that this probability of outcome depending on both their inputs will be nothing but the collection of these probabilities. So this is Alice's probability of obtaining some m given her input x and the shared randomness lambda. And the next term is Bob's probability of obtaining his outcome by given his the input y, the preparation of Alice, that is called m, and of course the shared random variable lambda. And these lambda have to be summed up. So therefore this integral over lambda. And finally, they are allowed up to d possible, the outcome. So m is summed up from 1 to d. Okay. So then typically these probabilities which are labeled by PA, m given x lambda, this is called the encoding function, which is the result of Alice's preparing procedure. And PB is the decoding function, which is the result of Bob's measurement procedure. Okay. And of course, these have to be normalized. So they sum over all m here and sum over all bi here is equal to 1. So this is the case when Alice uses classical communication using pre-shared randomness. But now suppose Alice uses quantum communication with pre-shared randomness. So in that case, of course, Alice sets the quantum state, as we said, rho x, and this can depend on the shared random variable lambda. And the measurement outcome of this state, given effect m is performed, is nothing but trace of rho m. Okay, the standard quantum mechanics, Mond rule. And now again, we have to integrate over all the distribution of these hidden variables. And let us say that rho x lambda and m, this effect operator, can belong to a set B, which lies in the d-dimensional Hilbert space. So what we are fixing here is the dimension of the Hilbert space. So that we are fixing. Okay. So again, in a nutshell, what is a collection of rho xy, which says that the quantum state is sent by Alice upon input x and random variable lambda. And what is the set of m? M's are the measurement made by Bob for input y, random variable lambda. Okay. And of course, these are conditioned on Alice's preparation as well. So these are two different kinds of probabilities depending on what kind of mechanism Alice employs. And there is also another mechanism Alice can employ. So you can consider a scenario when there is no pre-shared randomness available between Alice and Bob. And in this case, the probability is simply trace of rho m. Okay. There is no business of any pre-shared randomness or hidden variable. Okay, so that is clear. So now from the above three categories, what you immediately actually understand is that any communication scenario or the probabilities of outcomes that you get in such a scenario is defined by a set of natural numbers. And what are these natural numbers? These are nothing but L, N, and D vector, when actually X, Alice's inputs belong to N, and Y, Bob's inputs belong to this set N, and By is the set of all outcomes. So therefore, this D is a D vector. So they can range from 1 to N. Okay. So this D can be different in general, D vector, from the dimension small d. Okay. So that just keep in mind. So now, depending on what kind of mechanisms have been used by Alice in sending this communication, so different sets of probabilities are obtained by d-dimensional communication. So classical probability I can label by CD. This is just this probability which was there in the earlier slide, this P. And similarly, there is the set of quantum compatibility. And now you can also say that if you do not have access to shared randomness, you can define another quantum probability coming from here, the first equation, which I can label as QD bar. Okay, D labels the dimension. And you can also have another thing. Suppose all your quantum measurements are compatible. Suppose Bob can only do measurements from a compatible set, whose definition I gave in a couple of slides ago. So if Bob chooses only a set of compatible quantum measurements, then and he gets some probabilities, then I can label that set as QD compatible. And similarly, if there is no shared randomness, I can label that set by QD bar compatible. So in this slide, this is just for bookkeeping so that you remember later on. I've defined 5 different sets of probabilities, all depend on the physical mechanism employed by Alice and Bob. So C stands for classical probability, Q stands for general quantum probability, Q bar stands for quantum probability without shared randomness, QC stands for quantum probability when only compatible measurements are used, and Q bar C stands for quantum probabilities for compatible measurements when there is no shared randomness. Okay, so now we are in a position to state one of our main results, that is measurement incompatibility is necessary for quantum advantage, and this we show that this is valid both with and without shared randomness. And in order to do so, first of all, we prove this result that given any scenario specified by the set of these natural numbers, first of all, this set of quantum probabilities without shared randomness, when you have only compatible measurements, is a subset of the set of quantum probabilities when with the shared randomness when you have compatibility. But the most important, the more important thing I should say is the second relation, that is the equality, which we show here, is that the set of classical probabilities is exactly equal to the set of quantum probabilities employing compatible measurements. So already you can have a hint. We are saying that whether you employ a classical mechanism or whether you send a quantum state but you only employ compatible measurements, you do not get any difference whatsoever. Okay, so let me just skim through the first part of the proof. The rest is there in the paper, those of you like. So the first relation is actually very trivial because this follows from the definition of the two sets. So the set of all compatible quantum measurements can be taken as a general set, whether or not there is any shared randomness. So this is rather trivial. So now for proof of the second relation, so consider that Bob performs POVM measurements from the parent POVM set, right? The way we define. So the marginals of the parent POVM set will give rise to all compatible measurements. So if Bob performs measurements from the parent POVM set, then we apply a very famous result, which was published in 2015. It is known by the Frenkel-Wiener theorem. And what does the Frenkel-Wiener theorem state? It states that if you have a single quantum measurement on a d-dimensional quantum state, then the set of input-output probabilities, that is P-output kappa given by input x, can always be reproduced by suitable classical d-dimensional communication with shared randomness. So what this theorem states is that in this particular context, that if you define the dimension of the system, then if whether you have a classical state with the shared randomness or you have a quantum state does not make a difference, but only for a single quantum measure. Okay. So now in this set of GK, we will apply this Frenkel-Wiener theorem. In what way? Exactly as follows. So let us say that you have any arbitrary quantum state rho x conditioned by some lambda. Okay. So now we claim that there exists a hidden class, there exists a classical strategy, and how such a classical strategy is defined is by the following functions. One of them is again using some random variable, which I label as phi tilde, lambda over lambda tilde to differentiate from the original lambda here. then the set of encoding and decoding functions. So classical strategy for what? To enable success in this game that we are talking of in the prepare and measure scenario. So we need to specify Alice's encoding function, Bob's decoding function, and then the output is nothing but for a single quantum measurement, it is nothing but rho gk, trace of rho gk, and which is again nothing but just this classical probability. If you remember what I wrote in a couple of slides ago, so the right hand side is the classical probability. But remember the left hand side is trace of rho gk. Okay. So herein we get this the result from the Frenkel-Wiener theorem. So now what is the next step of the proof? So next consider that this arbitrary probability distribution actually that we have defined, it belongs to the set of compatible measurements because we've already chosen this parent set GK from which all marginals are compatible. Okay, so this then can always be reproduced by a suitable classical strategy that we have to show. So for that purpose, again, you consider the set of probabilities which falls under this compatible set. And then this is labeled by from the earlier definition that I showed in the last slide. So now, of course, again, using the Frenkel-Wiener theorem, I can say that it comes from a set GK for such that for all by, y, and lambda, this measurement effect is a sum of these probabilities times GK. Okay. So if you plug this inside here, what you get, this function immediately turns out you come here. And next step is where you actually apply this Frenkel-Wiener result. That is, you can reproduce such a single outcome. So you take the outcome by outcome in the sum, and for each outcome, each measurement, you apply the Frenkel-Wiener result. And finally, lo and behold, you get this, this expression. But what is this expression? This is, if you remember, go back a few slides, this is nothing but it labels the probability of something which belongs to this classical set of. So what we have been able to prove is that this set of probabilities which come from compatible quantum measurement are a subset of these set of probabilities which come from a classical measurement. So this is one relation, but now we will prove the vice versa, which is again sort of trivial. So the second part of the proof, what we show, that any classical strategy can always be realized with a quantum strategy of compatible measurement. So this you can easily satisfy yourself that whether you send a classical set of variables or you apply some quantum measurements, where if they are compatible, then you can actually see that these form a subset of all classical compatible measurements. So once you have these two results, that is QC subset of CD as well as CD subset of QD, then what do you get? Then of course these two sets are identical. So nothing remains, okay, between them. So what we proved here, that the set of probabilities obtained from a set of compatible quantum measurements is exactly equal to the set of probabilities obtained from a classical strategy. So let us try to now classify. Also, remember, I actually listed out 5 probabilities, and there are other results, of course, we prove in this work for all those probabilities, but I will not bore you with all the technical details of the proof. But let me pictorially describe to you what we actually derived with. Okay, finally, the complete set of results. So, but remember, essentially, so the figure of merit in any communication task is the function of these probabilities depending on input, output, and the message sent. And any quantum advantage in such tasks that you can obtain, that is both true with or without shared randomness, is obtained only if the set of measurements is incompatible. So that we already proved, because if the set of measurements is compatible, then you exactly mimic a classical strategy. So in order to obtain quantum strategy, you have to have a set of incompatible measurements. So incompatible measurements are necessary for quantum advantage. So now once we prove that, we further prove some generic relations between various probability sets. So as you can see from this figure, so QD bar, that is quantum set without shared randomness, is not a subset of these sets, that is the classical set, but it lies outside. But the more interesting and important thing is that if you take the intersection of, say, CD with QD bar compatible, okay, so QD bar generally, and you filter it out with QD bar compatible, this is not a null set. So what we mean here is that the quantum set of compatible measurements without any shared measurement is not simply the subset of the classical set and the quantum set without shared randomness. And essentially from our analysis, we again prove another result which appeared in PRX Quantum in 2021 by Chavez et al. What they showed was measurement incompatibility is not sufficient for quantum advantage without pre-shared randomness. So from our general analysis, we are also able to prove such a result. Okay. So now let me briefly allude to you what is witness in this scenario, or given a general set of measurements, how can you figure out whether those set of measurements are incompatible or not? Okay, so this is a brief, quick recap. So we have n measurements defined by m. So this is the prepare and measure scenario. Y these inputs, okay, inputs for Bob, and Di are the outcomes. And Alice gets a string of n bits, which are labeled by x1, x2 to xn, randomly, and from the set of all possible strings. Okay, so these are strings. Alice communicates a d-dimensional classical or quantum system, encoding her information without classical randomness. And Bob's task is to guess the white bit when y is chosen randomly. So this is the task. And in such a task, how can we certify from the probabilities whether the measurements employed by Bob are incompatible or not? So we make use of a witness, and the witness actually comes out to be a function of this generalized figure of merit that I told you earlier. So any communication task is defined by the set of these classical numbers, and the general figure of merit for a generalized such communication task is nothing but a normalized sum of such probabilities. So probabilities can be anything, quantum, classical, whatever. So in this context, what we show, this is another result that we prove, that given any general scenario specified by Ln and D vector, the maximum values of any linear function of P, that is obtained from the three different sets, that is classical set, quantum compatible, and quantum compatible without randomness, are all the same. Okay, so the maximum values obtained for all these sets are the same. So which is stated down below here. So S classical is equal to S with compatible, and also S quantum with compatible without shared randomness. So the maximum values of probabilities are the same. And just remember, our task is to maximize this figure of merit. So indeed we can do that, but before that we have to obtain the classical bound, and this classical bound can easily be obtained. So due to the lack of time, let me not go through the further details of the mathematics. Those of you can ask me later. But again, the classical bound is nothing but a function of these probabilities when you use the classical mechanism. Okay. So now, when we have these results, so what we can show is that whenever a set of measurements in the specified scenario gives this figure of merit which exceeds the classical bound in a general RSC game, then we can conclude that the measurements are incompatible. So what do these S depend on? They depend on probabilities, and the probabilities actually you find out by performing measurements by Alice and Bob. So these are measurable quantities, and whenever such measurements leads to this sum which is greater than the classical bound, then you can certify that the measurements performed have indeed come out of an incompatible quantum set. So this is the meaning of incompatibility witness. And of course, again, we can recover back results corresponding to the very elementary RSCs, that is 2-to-1 RSC, 3-to-1 RSC. Not only that, we also show that if you have any set of three incompatible rank 1 projective measurements, they automatically lead to values which is greater than the classical bound, which in this case is 3/4. So actually, this recovers back results by Hainosari Horodeki in 2020. Okay, from our general formalism. So finally, very quickly to summarize, before the last 5 minutes, I'll come to the next part. To summarize this part of the talk, what we have discussed here is that if you have a typical prepare and measure scenario, which is played by two parties, then incompatible measurement at the receiver's end or Bob's end are necessary to demonstrate quantum advantage in any communication task. Okay. And what we have done here, we have characterized the set of quantum correlations produced from the set of incompatible measurements in the prepare and measure scenario. And we have obtained the relationship between various probability distributions. And this allows us to actually formulate semi-device independent witnesses of measurement incompatibility. And this process, we actually, our results in specific context give rise to many different, very recent results in this subject. Okay. So now I come to the second part, and I will just skim through it because time is
just one brief question.
Yeah,
Archan.
sure.
So preparation is not necessary to have, prepare in, there is no role of MI in preparation.
Yeah, in the way which I have discussed it, actually, the measurement incompatibility at the receiver's end is very important. But that does not rule out the, say, if you come to things like preparation contextuality. So that is also a very interesting, nice subject.
Okay.
So even using preparation contextuality, people have been able to show various advantages in communication tasks.
Okay.
But our result is limited to incompatibility by the measurer.
Okay.
So only if the measurer has incompatible measurement, then it leads to general communication advantage.
Okay.
Okay. So now let me very briefly describe the next part of the task, and the essence of it is communication without entanglement, as I was discussing earlier. And basically, again, for the benefit of students, what is quantum communication? Quantum communication is the art of transferring a quantum state from a distant location. Say Alice has a quantum state and she transfers it to Bob. Okay. And in the process, since you know there is a no cloning theorem, the state can't be copied. So Alice's copy essentially gets destroyed. Okay. So now the BB84 protocol is a very typical example of such a task in the prepare and measure scenario, right? And so BB84 has been technologically demonstrated. So this even more than 20 years ago, they could achieve this QKD, secure QKD over say nearly 70 kilometers under Lake Geneva. So all this is old stuff. So now we ask the question, since we talk of contextuality, so what is the status of quantum contextuality in scenarios without entanglement? Okay, so even before us, people have pointed out beautiful applications. So one of them is quantum state discrimination. So it is a very interesting topic. Let me leave it out. The another one is something which is called robust self-testing of quantum theory using contextuality, that is non-contextual inequalities, violation of non-contextual inequalities. And this is also a PRL paper of 2019. And by self-testing, what we mean is that if we have an unknown state and measurements, just performing some measurements and from the outcome probabilities without having direct access to the measurement device or the states, can we certify entanglement of such states, or can we certify the proper measurement use? So that is which is called robust self-testing. And any actually application of contextuality relies on this mathematical graph theoretic framework, which I have underlined for the sake of our subsequent analysis. So whenever you want to actually discuss, apply contextuality, the very useful way is to go through the graph theoretic framework. Right. And secondly, also another case where the contextuality is very interestingly useful is in quantum computation. And actually this provides all the power to quantum computation. And in this case, there is no entanglement. So this is what drives quantum computation is again contextual. Okay, so in this scenario, there are other examples as well. For example, contextuality monogamy. Using contextuality monogamy, you can have a secure QKD, and Arvind and collaborators have demonstrated it. And also, you can have preparation contextuality, actually what Prasanta was just asking. So at the preparation level, if you have contextuality, then you can also apply it in several interesting tasks to get quantum advantage, and one such task is parity oblivious multiplexing. So we ask this general question again: how is contextuality in general related to advantage in quantum communication? And before that, very quickly, just to advertise it to students. So these are a very informative, very enlightening set of slides by Kubczynski. So which has the title "Contextuality as the Key to Understand Quantum Paradoxes." Those of you who are interested can have a look. And how to derive, how to define contextuality actually very qualitatively. So in that, we distinguish between two types of properties a physical system have. So a physical system can have an attributive property, which we say is a constant property and object, which can be observed and measured at any time, which is not modified by measurement. What are the typical examples? For example, rest mass or electric charge of a particle can be said to be an attributive property. In contrast, a contextual property is a property that is revealed only in specific experiments or under particular condition that characterizes the interaction of the object with the external world as well as the measuring apparatus. Okay, so typically you can think, say, in the classical world. So for example, if you have a chameleon, the color of a chameleon, if you have a weight, how you are weighing it. And in quantum mechanics, you can typically think of spin projection, depends on which direction you are measuring, probabilities, so on and so forth. So all quantum probabilities, by the way, are contextual probabilities as emphasized by Marian Kubczynski, right? Okay, so this is the slide. So actually, how does probability arise even in a classical context? If you take a typical coin tossing experiment, so there is a coin, but there is also a flipping device. So such probabilities arise not only as just the inherent function of the coin, but also the action of the flipping device. So now in quantum mechanics, the context is very clearly defined by the following probabilities. So if you have, for instance, a pure state preparation in Hilbert space, and you want to measure an observable A, which is a self-joint adjoint operator, then you need an experimental setup to measure A, and that is labeled by E. So together with psi and A, this experimental setup E actually defines for you the context of any measurement. And by the way, contextuality is again extremely important and useful for understanding very different kinds of phenomena. So just very quickly, if you look into the slide, and those of you for historical reasons, of course, many of us have studied more about Bell's theorem and local realism. So we can understand it better. So local realism, or in other words, counterfactual definiteness, what does it tell us? It tells us that measuring devices register values of physical observables which are existing independently, whether they are measured or not. Okay. In contrast, what is contextuality? Contextuality tells us the values of contextual physical observables, such as spin projections, are created in the interaction of physical system with the measuring apparatus. Okay. So without actually this specific context, there is no meaning. So they do not exist even without measurement. And you can immediately see that violation of CDF, counterfactual definiteness or local realism, that is manifested by Bell locality, is nothing but the application of contextuality for specially separated entanglement systems. Okay, so some people will say that contextuality is the basic formula. So again, this is the, so by the way, I think I'm running out of time. How much time do I have? Doreen?
Yeah, it's few minutes.
I have run out of time. Okay. So, yeah, okay. So let me skip through the technical definitions of contextuality, some simplest examples. Quantum contextuality in practice. Okay, so very briefly, in a few seconds, I describe our recent work, which is published in PRL. So what we show here, the title is Quantum Contextuality Provides Communication Complexity Advantage. And what we essentially show, the first important result, that if we take any arbitrary quantum state and observables, and this is a technical specification, and thus we take such quantum state and observables which produce quantum contextuality. If any arbitrary set of quantum states and observables produce contextuality, then we show that there is indeed a communication task with quantum advantage. So there is one-to-one correspondence, two-way correspondence, that if you have an arbitrary quantum state and observables which are contextual, which produce contextuality, then automatically there exists at least one communication task with quantum advantage over classical. Okay. So this is, then you can argue that the same thing you said for measurement incompatibility. Completely true, but contextuality, the basis of contextuality is measurement incompatibility. But if we stop here, then of course this will not make a PR. So what we show further is that not only this contextuality can be seen as the driving force for such quantum advantage, but using contextuality, you can also show another beautiful result. That is, if you consider a general communication task, then there is something which is called communication complexity. That means that given a scenario, classical, quantum, or whatever, how many sort of communication inputs you need to actually play this game or achieve success. So what we show that the difference between classical and communication complexities increases polynomially as the number of input grows. So this is a definite hallmark for the quantum advantage of a task, which is driven by nothing but contextuality. And we show that for all such tasks which are driven by contextuality, one can have a protocol for quantum key distribution. Okay, so these are all the details which unfortunately I couldn't go through. And so let me just skip all of them. So let me just finally come to the last slide. So in this talk, which what I wanted to convey here is that we ask the question that at the fundamental or basic level, we know that there is advantage in quantum communication beyond classical. So what drives such advantage we show is measurement incompatibility. So MI is a fundamental quantum resource for non-classicality in communication tasks. And indeed, what we have to do in quantum information by the community, we have to have a resource theory for MI, which is still not there. Okay. And what we show here is that the violation of the classical bound of any communication task is sufficient to witness measurement of incompatibility. So this way is necessary, the other way is sufficient. This is easily understandable. And finally, what I just read to you, I had no time to show that any quantum state and observables that produce contextuality actually lead to quantum advantage in communication. And by the way, this is a two-way result, of course, with some technicalities, with some assumption, technical assumption, but that too in a broad general context. And finally, this one is extremely significant for applications that as the number of input increases, the ratio between classical and quantum complexities increases polynomially. And where can you apply them? This can be applied ubiquitously to the so-called equality problems in quantum computer science, when you have, say, large data sets. And to begin with, you have to, say, for example, figure out whether these data sets are identical or whether errors have crept in to make them non-identical. So you can apply an algorithm here, and a classical algorithm will consume huge amount of computer memory, whereas a quantum, due to this result, any quantum algorithm which makes use of contextuality, which will consume much less memory. Okay. So what are the future directions? What are the spin-offs? Of course, we have defined weaknesses, but definitions is not enough. To implement practically, we need more efficient weaknesses. Then also we can take this forward. So we have actually done this analysis for quantum states, but we can define incompatibility for channels, for instruments, and finally on the side of applications, what I said are just words, but one can take it out and apply and show real advantage in equality problems, for example, in problems involving more than 2 parties. So thank you very much, and sorry for overshooting my time. Thank you.
Thank you very much, Ashanda, for this very enthusiastic talk. The floor is open for questions.
May I ask a question, sir?
Yeah, please go ahead. Sure. Yes.
Yeah, so in the first part, you said that measurement incompatibility is a necessary resource, or is necessary for quantum advantage in RAC task. So
Yeah.
isn't that the result of that Carmeli paper in Europhysics Letter 2020? I mean, how is it your result different, or does it say something more?
Yeah, of course more, because we have done it in the context of a general communication task, not just 2-to-1 RAC, but general RAC, which are defined by 3 sets of numbers. Okay, so all the
for
other
any ND, it is like generalized
yes,
to all
yes.
Okay.
So we have shown that it is necessary in the general context. Yes.
Okay, and also in the second part, is this contextuality different from Speken's contextuality?
Yeah. So this is basically Cochin-Specker contextuality, measurement device contextuality. Speken's contextuality is typically labeled to what Prashant was actually saying, that is preparation contextuality. So at the preparation level, you can have your preparations to be contextual. So as I said very quickly in one of the slides, that has also been shown to lead to interesting quantum advantages without entanglement, that is parity oblivious multiplex. But here we are sticking to the sort of measurement contextuality, if you like that sense, which is given by Cochin-Specker, Cabello, Klachko, et al. So on and so forth. So we are in that context, we are showing a general result that any quantum state and observables which produce contextuality in measurement, okay, in that sense, will lead to quantum advantage in communication. And if you find any quantum advantage in communication, you will naturally be able to certify such a scenario involving measurements to be contextual. You cannot get such advantage in communication within the non-contextual scenario.
So it is true for all communication tasks. Like if I have
of course. I must classify here a little bit because I didn't have time to go through the details. So by the way, communication, I mean communication, one-way communication in the prepare and measure scenario. Okay, so I have lost the slide. One-way communication in the prepare and measure scenario. And the first one-way result that we prove is quite general, and the other way result which we prove is up to a technical subtlety. Okay, so we show that whenever the dimension, let me come to it, where is that? So whenever the quantum Hilbert space dimension, where am I? Okay, quantum Hilbert space dimension is less, okay. So let me show it graph theoretically. Okay, so whenever the quantum Hilbert space dimension is less than equal to the chromatic number of the graph employed, and what is the chromatic number? This is the smallest number of colors needed to color all the vertices so that no two adjacent vertices are with the same color. So if you look into the Klachko problems, KCBS famous inequality, here we are. Okay. So this KCBS famous inequality, so this is done by the 5 vertex graph. And by the way, all adjacent vertices describe measurements that are incompatible. So for example, these pi2 and pi0 here are compatible. They are not adjacent. So how many colors do you require to color this graph? So that basically means how many compatible measurements can be there. So how many colors you require so that no two adjacent vertices share the same color. So if that number of colors is strictly bounds the number of Hilbert space dimensions, then we are able to show the converse result. Okay, but the one-way result is pretty general. And again, for lack of time, I could not show. So there exist examples of state-independent weaknesses which were actually demonstrated earlier in these references. And here, just look at the advantage of classical over quantum. So if at least this is of the order of 10 to the power of 13. Okay, so Hilbert space dimension 3, Hilbert space dimension 3, Hilbert space dimension 4. Okay, later on if he improves, you have advantage ranging over, that is the ratio of classical to quantum communication inputs required is of the order of greater than 10 to the power of 13. So you can just figure out how much, if you are able to apply it in a practical context, how much advantage it will give you. So I hope I have been able to answer your question.
And the thing is that when you certify contextuality, it means that it is doing it device independently.
One-sided, one-sided. So
okay.
we are in a prepare and measure scenario. So one side is a black box, Alice. Okay, the other side is box. So in a prepare and measure scenario, by definition, it is one-sided measurement, device independent. So we take the probabilities and we certify.
Okay, thank you.
Any other questions?
Yeah. So, like I would like to ask, like, what is the significance of shared randomness in defining incompatibility of measurements? As in, these studies are being done in the context of like with and without shared randomness. So just, or what is the significance of it?
Yeah. See, so per se, directly shared randomness has nothing to do with measurement incompatibility. So measurement incompatibility you can regard as a resource, different resource, with or without shared randomness. But shared randomness is also a resource, but this is a classical resource. Okay, if I come back to this one of the earliest slides which I said. So shared randomness can be viewed as some kind of a resource which Alice and Bob have access to in general, without any quantum mechanical device or quantum mechanical states or quantum mechanical sources. So this can exist in the classical world. Okay, so even if they share a say common environment, for example, or they share say a mixed state without any say quantum resource, then also they have access to this shared randomness. So unless they reside in a vacuum or you deliberately remove it, you cannot rule it out in a very general scenario. So you have to take this shared randomness into account in a most general scenario, but by some methods you can actually exclude it out. So what we have proved that the quantum resource of incompatible measurements is actually a resource in both these scenarios when you have shared randomness, as well as in scenarios when you do not have shared randomness, right?
Okay.
Does this answer your question?
Yes, sir. But
Yeah.
like, like there was a paper that in your slides, there is a paper like by Sevels.
Yes.
Like
Yes.
this is the.
Yeah.
It says that incompatibility is not sufficient without pre-shared randomness.
Yeah.
But if we include the pre-shared randomness, then what would be the scenario for the measurement incompatibility?
Yeah.
Like, would it be sufficient?
Yeah. So that is something in general we have not yet proved in this work. So I cannot claim that. So that is one more direction. So to prove it sufficient in the most general scenario. So we have only proved it is necessary. Whereas Chavez et al.'s result, where they showed it is not sufficient without pre-shared randomness, actually follows from this pictorial representation of this set that we've shown. So this result actually follows again from our analysis. But in order to prove it, we have to show it very specifically that it is indeed sufficient with shared randomness that we have not been able to show in this work. So this is a one-sided.
Okay. That's it, sir. Thank you. Thanks a lot.
Yeah. Thank you.
Any other question? Any other question? If not, Maria, I have a small question. The last slide.
Yeah, sure.
You said it before also in your paper. How do you define this? So you're saying that the complexity increases in a polynomial as a polynomial.
Yeah.
How do you define complexity?
Yeah. It's a good question. I'm extremely sorry. Actually, there were too many slides, or maybe I focused on the first part because I thought that was to enable students to understand, at least take away some message. But these communication complexities, all, of course, we need to use mathematical definitions and we need to define them. So here we are. Okay. So just if you give me a couple of minutes I'll describe you this slide. So again, S is the figure of merit in this task, and we have taken this task under some assumptions. So it simplifies to the sum of these two probabilities, wherein, okay, so Bob gets an outcome 0 or 1 conditioned on the inputs, his inputs and Alice's inputs, and same here, Bob gets probabilities 1 conditioned on his and Alice's inputs. Okay, so now our task is to maximize this figure of merit, and under these kinds of assumptions from where we get this result, you can say that if we can achieve SG equal to 1, that is maximum SG possible, this figure of merit. G, by the way, defines the graph that we used here. And now we ask the question, what is the minimum dimension of either the quantum system or the classical system, labeled respectively by, say, Q of G and C of G, such that you can have this figure of merit maximized to 1. Okay.
Yes, and here, Archana, here,
yeah,
what does, I mean, I understand what is QG, but what is CG? What is dimension of classical this thing?
okay.
What do we mean by dimension?
Okay. So just go back and look at the communication tasks. So we are sending Alice actually encodes her task in a quantum system, or she can do it in a classical system. Okay, classical string. So basically, so when the classical probability, which I defined with spending some time in one of the early slides, actually follows from the mechanism when Alice employs a classical system to encode her message, right?
But should I understand it in terms of dichotomic observables that in a classical, that's how you count dimension? I'm just wondering what is the dimension?
Yes.
That's how one should count it. I'm just trying to.
Okay. Yeah. See, classically, it may or may not be dichotomic, but the number of, basically, you can say the number of classical strings she communicates to Bob. Okay. That labels the classical type. The classical, or you can say classical bits, she communicates.
I see. Okay. So in terms of binaries, basically.
Basically, you can regard
how many independent binaries do
she communicates to Bob. Okay, so that is the classical system. Okay. So now, in order to maximize this figure of merit, if you take the minimum dimension, that is the minimum dimension, minimum number of vertices of this graph, GM means M times G, this graph G. So you can see that this ratio C by Q actually exceeds this function chromatic number, which actually follows from the contextuality. So in this way, you say that the communication complexity required in a classical protocol is much larger than what is required in the quantum protocol, and the ratio actually increases polynomial with the dimension D. Okay, so the gap between quantum and classical can indeed be very large in larger dimensions, right? So this is what we show here.
Thanks a lot. Thanks for explaining. Yeah. Okay. Any further questions? No? Okay. If not, we thank again Professor Majumdar for his nice talk. And